microscopic. Okay, I will try to. I will give
Explain today.
a brief explanation of the theory. Okay, what we can model here. Okay.
Yes, right. Yes, now there are more and more people that perform calculations joining these experimental groups. It's very,
Yeah, yeah,
very
yeah,
smart
yes,
to work
yes,
together.
exactly.
We have- Some people are joining. Felipe. Felipe Espinosa, I guess, from Universidad from San Sebastián, from Chile. Ah, de Chile.
Hola Gabriela, ¿qué tal?
Hola,
Hola,
Felipe.
Hola.
sí, hola, ¿qué tal? Sí, de Chile, sí, sí.
No sé si de, de Chile, Puerto Montt. Ah, yo viví en Bariloche, ahí éramos medio vecinos.
Ah, sí, súper cerca,
Sí,
está
íbamos
como
acá.
a 400 kilómetros por ahí.
Claro, cruzar la montaña,
Sí,
¿no?
sí, cerquita. No he ido, pero eh, ya uno de estos días voy a ir para ahí a
Sí,
darme una vuelta.
sí, es
Sí,
cerca, claro.
sí, está al lado, sí. Tú estás en Córdoba, ¿cierto?
Ahora estoy en Córdoba, sí, sí. Más
Ya,
arriba, más lejos ya.
ya.
Creo, tengo entendido que el que va a arrancar las moderaciones, Arturo.
Arturo se supone, sí.
Sí,
Yo ya
Arturo
le
comenzó
escribí,
y yo
yo
voy
le
a leer.
escribí, pero no sé si.
No lo
Es
estoy
que él está
viendo.
en México.
Arturo está en
Y
México.
allá, sí, y allá van a ser
Está-
las 7:30, entonces,
es complicado, ¿no?
a
Sí,
ver,
sí.
sí, claro, sí,
Nosotros es más
les ha
fácil.
dicho eso, esperemos.
¿Quién más está? Ahí entró Luis. Hola,
Hola, profe
Luis.
Gabriela, ¿qué tal?
¿Qué tal?
Arturo aún no se conecta, ¿cierto?
No,
Ah, ya, sucede que Arturo es muy temprano para él.
claro. Sí, sí, sí.
Sí,
Terriblemente temprano para los
en
mexicanos.
México hay dos zonas, una zona que son las 6:30 de la mañana y otra zona que es 7:30 de la mañana. Entonces, va a entrar a las 7:30.
Claro.
Entonces, la situación es que no sé en qué zona está Arturo. No, él está zona este. Si es zona este, entonces debería estar 7:30, ¿no es así? 7:30 de la mañana, me parece.
No
7:30.
sé.
Sí.
Temprano.
Está cerca de Monterrey, así que
Exacto, está
van
cerca
a
de
ser las
Monterrey.
7:30 van a ser.
Exacto, sí. 7:30. Perfecto. Buen día, Albano.
Olá, olá,
Eh,
Luiz.
¿Todo bem?
Tudo bem?
¿Você é brasileiro ou você é português?
Sou brasileiro, natural do Brasil, né?
Ah,
E eu moro em Portugal, né, há 6 anos.
perfeito, perfeito.
Mas eu sou. Meu pai é português, meu pai. Mas moro
Ah,
no Brasil.
ok. Eh, Buenos días, Jaime Llanos.
Hola,
Jaime.
¿qué tal? Buen día.
Lá.
¿Qué universidad es Jaime Llanos?
Universidad Católica del Norte.
Mucho gusto.
Mucho
Mucho
gusto.
gusto. Perfecto. Bien, Albano, el día de hoy, eh, yo no soy el moderador, yo soy el secretario de la red.
Sim.
El día de hoy, eh, Arturo Martínez y Gabriela Grat son los moderadores,
Ahí
¿no?
entró.
Y acaba de entrar Arturo Martínez, por fin. Ya entró Arturo Martínez, perfecto. Entonces, Arturo, como queda, tiene más tiempo en la red. Entonces él conoce toda la tónica y creo que se ha puesto de acuerdo cómo va a moderar con Gabriela, que el día de hoy es su primera moderación también, ¿no? Entonces Arturo queda básicamente en sus manos y guiando a Gabriela. Yo voy a estar en el background, ¿ok? Todo tuyo, Arturo. Arturo, tu micrófono.
Sí, está apagado el micrófono, Arturo.
Ya, todo. Sí, ya, sí, sí. Buen día, ¿cómo están?
Todo tuyo, Arturo.
Sí, ya vamos a empezar a grabar. O...
Faltan 5 minutos. Sin embargo,
Ah,
con Gabriela, te estuvo mandando mensajes.
Y sí, nos hemos conectado y ya quedamos de acuerdo en que él comienza, después sigo yo.
sí, claro.
Ok, perfecto.
Sergio,
Hola, ¿qué tal? Buenos días, ¿cómo están?
buenos días, Sergio Conejeros.
En esta oportunidad invité al profesor Jaime Llanos porque él tiene expertise en lo que son lantánidos y yo creo que va a hacer un par de preguntas que podrías estar bien para el invitado.
Perfecto,
Buenísimo.
perfecto.
A mí me parece que Albano habla un poquitito español, me parece.
Portuñol, quizá.
No, 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 portuñol.
Bueno,
¿Vos es pernambucano?
Sí,
Ah, por eso vos conoce a o amigo Augusto Moreira.
no, no, no.
Ah, ya, porque Augusto fue que contactó con vos. Augusto
Augusto.
Moreira. Augusto
Não,
Moreira.
foi Júlio. Júlio. Julio.
Ah, ya, otro rapaz.
É.
Entonces, sí, Augusto Moreira de la Universidad Federal de Pernambuco, en sede en Caruaru. Perfecto.
Ah, em Caruaru. Sim, sim,
Sí.
sim.
Bien, yo no distraigo más. Voy a estar en el background, ¿ok? Voy a estar en el background. Ok. Perfecto,
Ok.
Gabriela y Arturo. Saludos.
bueno, saludos. Todavía queda un ratito, ¿no? ¿O ya comienza? ¿Ya comenzó a grabar todo? ¿Comenzó a
I
grabar?
think you have some minutes. So,
Sí,
go ahead.
a las 10:30 hora de Brasil empieza, hora de Argentina.
Faltan 3 minutos, ¿no?
Sí, faltan 3 minutos.
¿Qué hora es en México, Arturo?
7:30.
Es- Arturo es bien fiel, ¿ah? 17:30 de la mañana, sábado.
Sí, sí, tremendo. Y si saliste el sábado viernes a la noche está complicado.
Se complica, sí, se complica. Bueno, y en algunas partes del país son 6:30. Por ahí cuando se conectaba nuestro compañero, pero ahora está en Perú, ¿no? El Francisco Paraguay, él
Allá.
se despertaba a las 6:30.
Ah, vi hace unos días atrás a Miriam Mejía. Estuve en Perú. Estuve
Ah,
en Perú hasta la semana pasada, hace una semana, y estuvo Miriam Mejía. Creo que ha llegado por Navidad, Año Nuevo.
sí, sí, se va a quedar por allá hasta
Sí. Yo pienso viajar a Perú.
un mes y medio.
Estoy en Inglaterra, estoy en Cambridge, y pienso viajar a Perú ahora para Navidad, Año Nuevo. Pienso pasar por allá. Sí.
Ah, qué
Bien.
bueno.
Ok, ya, demasiado estoy hablando. Quedan ustedes.
Ahí entró Mario Reis. Mario Reis de la Universidad de Brasil. Hola, Mario.
Hola, ¿todo bien?
Olá.
Aquí estamos por empezar la
Universidad Federal Fluminense.
Mario Reis. Bien. Ah, Fluminense, Brasil, sí, claro. Bueno, yo creo que ya, Arturo, si querés comenzar con la presentación de la red, ya estamos, ¿no?
Ya estamos.
Casi en
Vale.
hora.
¿Ahora quién está? Para empezar a grabar.
Ya, me da un momento, profesor. Buenos días con todos. Un momento, unos 30 segundos, por favor.
Estamos ansiosos todos.
Listo, pueden comenzar.
Sí, buenos días a todos. Estamos aquí reunidos en la red latinoamericana de materiales, la red LabMat. Nos reunimos como cada sábado con universidades del sur del continente, con Chile, Argentina, hasta el norte, con México. Eh, También tenemos países como Perú, Brasil y, y tenemos hoy la plática del doctor Albano Carneiro, Neto, que nos presenta la plática From Theory to Experimental Validation, Redefining the Neodimio issue Energy Transfer. Él es del Departamento de Física de la Universidad, del Instituto de Materiales de la Universidad de Aveiro, en Portugal. Pues adelante, you can start, Albano.
I can share with you the presentation, some other topics of the curriculum vitae of Dr. Albano Carneiro. He earned his Ph.D. at the Federal University of Pernambuco, Brazil, under the guidance of Professor Oscar Malta in December 2018. He's currently a researcher at the University of Aveiro, Portugal, and a prominent expert in the theoretical modeling of luminescent materials with a focus on lanthanide-based compounds. His academic record includes 78 published articles and 7 book chapters, accumulating over 2,200 citations and an index 27 according to Google Scholar. Dr. Carneiro has presented his research at numerous international conferences addressing topics such as energy transfer involving lanthanide ions, emission simulation in nanoparticles, and the modeling of luminescent nanothermometers. In recognition of his contribution, he was named among the world top 2% most cited scientists in 2022. Well, okay, his talk, as was said, is from theory to experimental validation, redefining the neodimio 3+ to iterbio 3+ energy transfer. And thank you, Albano, for being with us.
Okay, can you hear me?
Yes.
Okay. Good morning. First, I'd like to thank Arturo Martinez and Gabriela Grad for the kind introduction. Well, as Gabriela mentioned, I'm specialized in theoretical calculations on energy transfer and luminescence spectroscopy, particularly involving lanthanide ions. Okay. So today I'm excited to share a topic that recently called to my attention, that is about the energy transfer between neodymium to ytterbium ions. And this case is fascinating because it challenges what is commonly reported in the literature. So unlike other lanthanide pairs, for instance, I will give you some examples. And the energy transfer between neodymium to ytterbium behaves differently, okay, from the others. And I will try to explain this and the reasons of this behavior, okay? Okay. Well, let me explain the energy transfer process with this simplified energy diagram, okay? When you excite a donor, here represented by this written phi, energy can flow from the donor to the acceptor, but only in specific conditions is required to this happen, okay? And this process is fundamentally different from charge transfer. It's totally different, which involves the transfer of electrons. Here, in the energy transfer process, the populations of the donor excited states decays non-radiatively from a state, in this case alpha, to the state beta, and at the same time, the population of the acceptor rises to these excited states 2, for instance. And in this example, the emission intensity of the acceptor here, this I21, can be calculated through the population of this, the emitting level, times the relative component, or the Einstein's emission coefficient, okay? Now I'll give you some historical context. Well, the concept of energy transfer, specifically involving lanthanide ions, started in 1942, when Samuel Isaac Weismann demonstrated that the characteristic emission of trivalent europium could be excited indirectly by light absorbed through the organic parts of the compound. So this work sets the foundation for understanding the intramolecular energy transfer process in lanthanide systems, okay? So this was the starting point. In 1946, Theodore Foster laid the foundation for what we call Foster resonance energy transfer, or FRET. Foster described how non-reactive energy transfer between a donor and acceptor occurs through a dipole-dipole interaction. It means the dipole of the dipole transition of the donor interact with the dipole transition of the acceptor. Okay, I will talk later about the usage of the FRET in lanthanide compounds, and I can anticipate that I cannot recommend. In 1953, Dexter published his seminal paper, A Theory of Sensitized Luminescence in Solids, and Dexter extended the energy transfer concept to include forbidden transitions, okay, which are particularly relevant for lanthanide ions. In this work, Dexter highlighted that the efficiency of energy transfer depends not only on the overlap between donor and acceptor spectra, but also on mechanisms such as exchange interactions. However, I show here, he points out that the weak spectral overlap, as in the case of samarium ion, can limit energy transfer efficiencies. Okay. Well, in 1962, the field took a major step forward with the development of the Judd-Feld theory. This theory, that was developed independently by Brian Judd and George Feld, the same year, they never met each other, and they published 2 independent papers, and they raised the same conclusions. Was the groundbreaking work that the foundations of how we can understand FF transitions in lanthanide spectroscopy. Okay, basically, FF transitions are typically forbidden by the parity selection rule. Okay, but however, the Judd-Feld theory explained how this transition become partially allowed due to the influence of surround environment of the around the lanthanide ion. This equation shown here represents the Judd-Feld intensity parameters, which describe the electric dipole strength of a FF transition. This framework remains crucial for modeling and predicting photophysical behaviors of lanthanides, okay? And also, from the timeline point of view here, it's clear that both Foster and Dexter original theories do not consider the Judah theory to describe FF transitions. This is a problematic in the point of view for these two theories, Foster and Dexter. In 1973, Takashi Kushida applied the formalism of the Judah theory for the first time to explore energy transfer mechanism in some high-earth doped inorganic materials. Specifically, his work focused on calculating transition probabilities and identifying the dominant mechanism involved in lanthanide to lanthanide energy transfer. I show here Kushida introduced three types of energy transfer mechanisms: the interaction of dipole-dipole, as adapted from the Foster theory, and the dipole-quadrupole, and the interaction of quadrupole-quadrupole. When we talk about dipole-quadrupole, for instance, is a dipole from the donor and the quadrupole transition of the acceptor, okay? And in this study, Kushida concluded that the quadrupole-quadrupole mechanism is considered to play the dominant role in this iterbio to iterbio transfer case. In 1993, Peter Turner and collaborators introduced the magnet-dipole interaction. And so, as an additional mechanism that was developed by Kushida. And the magnet-dipole described the energy transfer by magnet-dipole interactions between donor and acceptor ions. While often weaker than electric-dipole interactions, magnet-dipole contributions are particularly relevant for certain transitions in lanthanide ions in systems where the lanthanide ions is placed in a symmetry with center of inversion. So, which was the case of this study. The symmetry is very important in lanthanide spectroscopy. In 2008, Oscar Malta, from Brazil, made significant contributions by revisiting and refining the energy transfer theories. And he expanded Kushida's equations by introducing crucial elements such as 4F Childer effects and a more precise calculation on the expected overlap factor. I will enter details of these terms later. And additionally, Malta introduced a new formulation of a Dexter exchange mechanism, specifically created for the case of lanthanide ions. These refinements address the unique characteristics of these ions, and this enhanced the accuracy of theoretical predictions so far. Of course, this timeline is a simplified representation of the advancement in the field. As you can see here, there are numerous contributions that have shaped our understanding of energy transfer process. For instance, in 1966, François Zell discovered the upconvection process, which brings a lot of applications in bioimaging and so on. In 2005, Andries Meijering from the Netherlands introduced the concept of quantum cutting by cooperative energy transfer. This also has implications in application as solar cells, for instance. In 2011, Xiaogang Liu made significant contributions by exploring energy migration process in core shell nanoparticles. So there are a lot of other contributions that I didn't mention here because we don't have time, but they are also important to the development of the theory and development of the field. Now let's discuss the FRET, the Foster resonance energy transfer, or fluorescence resonance energy transfer. Some authors use the fluorescence, and the others use the Foster in this case, okay? FRET has been crucial concept for understanding energy transfer in molecular systems, particularly when both donor and acceptor transitions are electric dipole allowed. This is very important to keep in mind, okay? So the donor can transfer to the acceptor, and in this case, involved the development of the Foster theory. He considered allowed transitions. For instance, for biomolecules, you can transfer energy from a donor to acceptor here. This is very dependent on the distance, okay, between the two centers, and when they are closer, we can see the energy transfer process, and also there is a resonant condition with the spectral overlap. Okay, so the donor emission could be very overlapped with the acceptor absorption. So this is the overlap. This part EJ is the overlap, spectral overlap between these transitions. So the rate is proportional to the spectral overlap, and the inverse is inversely proportional to the 6th power of the distance, okay, between donor and acceptor. Wire thread is a powerful concept for describing energy transfer in molecular systems where electric dipole transitions are allowed. The application of thread to lanthanide transistors is conceptually wrong, okay? I will show you why. And this rising, okay, primarily because the thread formulation lacks the Judah-Fett theory formalism, and as I mentioned before. And here we show that the number of published papers by year about thread lanthanide ions has increased over and over the years. Okay, in summary, thread is still important, but not for lanthanide ions. Okay, it's important for allowed transitions, electric dipole allowed transitions. And I would like to mention that Frost never studied lanthanide ions. So let's answer this question. What's a lanthanide? Lanthanide exhibit 4F transitions, which are technically forbidden by the Laporte selection rule. Due to this condition, the delta L is 0. And these forbidden transitions result in extremely low relative probabilities under normal circumstances, of course. Yet, as shown in this spectrum, we observe clear emission peaks from lanthanides, in this case for the European. So how can we explain these emissions? The answer lies in the Judah-Fett theory, which provides a framework to quantify the intensity of these transitions by account for the perturbation caused by the surrounding environment and the lanthanide ions, okay? This interaction, né? The Judah-Fett theory explains that 4F orbitals are mixed with 5D orbitals, becoming partially allowed. So there is a mixing between 4F and 5D that in such a way that the 4F orbital are not pure anymore. So in this case, this represent the mixture here, the mixture F4FN, 4FN 5D, and we can see some pathways that are allowed. For instance, this pathway to this and this to this, okay? And this makes the transitions allowed, forced, the correct term is. And lanthanides are also characterized by their 4F electrons, which are heavily shielded by the 5s and 5p. This is the distribution of the radial distribution of the electrons. And we see here that the 5s and 5p6 are complete shells here, and they are they shield the 4F electrons from the environment. So this is particularly important for the lanthanide ions. And this shielding leads to weak interaction between these four F electrons and the ligand field, for instance. Okay, and this shielding, and as a consequence of this shield effect, is that we can construct these kind of energy level diagrams, called Dix energy diagrams, that the energy levels of the 4F configurations are discrete, and they don't change too much in energy. So they are almost constant. The relative rate is determined by Einstein emission coefficients, and I show here, okay, through this equation, which depend on factor like the squared electric dipole strength, this SAD, and the magnetic dipole strength, this SMD. Okay, so as I mentioned before, in the lanthanide spectroscopy, this quantity is the electric dipole strength is defined by the Joule-Feld theory, where these parameters, omega lambda, is so-called Joule-Feld intensity parameters. So there are selection rules involved here in these transitions, and I will explain to you. But first, I would like to emphasize the order of magnitude of this electric dipole strengths. For instance, for the case of lanthanide ions, we see in comparison with spin-allowed transitions, for instance, fluorescence, we see that the electric dipole strength is 1 million times higher than the 4F transitions. Okay. Now I'll talk about some selection rules that govern the FF transitions. Okay, I will give some examples to make it clear. For the electric dipole transitions, this should obey these conditions. Okay, the difference of the J levels of the transition. These lambdas assume values of 2, 4, and 6, and it should be between these, the sum and the subtraction of the G levels. And for magnetic dipole transitions, the delta G should be 0 or plus minus 1. Okay, except in the case of where both J are equal 0. So let's take one example here. The terbium 5D475. Okay, the delta G is 1, so this is magnetic dipole allowed. And then for the electric dipole transition, we see this condition here. It contains the lambda 2, 4, and 6. So all the summation of that equation of SAD are present to you. This it has the 3 contributions for U2 matrix elements, U4, and U6. Okay, so all of components are allowed. But in contrast, the 5D471, this is forbidden by magnetic dipole, and there is only one contribution, okay, for the lambda 4. So this transition will be very dependent on the one parameter of the Joule-Feld intensity parameter. There are 3, okay? So in this case, all of these values of the major elements are tabulated, okay? In this paper by Carneiro, for instance. And we see here for the specific transition, we see here the major elements is 0 for lambda 2, is non-zero for lambda 4, okay, and 0 again for lambda equals 6, okay? So this is the selection rules that we need to take into account for our theoretical analysis. So, which transitions should be expected to be stronger? The 5D475 or 5D471? So the answer is this 5D475 This is totally allowed by magnetic dipole and electric dipole transitions. This is more allowed than this 5d4, 7f1. Okay, and we can see here the difference between density between each other. Well, now imagine that case where there is no acceptor present. For instance, for example, a crystal containing only iterbio ions, and in this case, the donor excited state alpha decays naturally with an emission lifetime tau d, which corresponds to the rate 1 over tau d. Now, when the acceptor is introduced, then the transfer becomes possible. This transfer leads to a faster population of the donor excited states, reducing the emission lifetime tau dA. So we have this condition. The tau dA is shorter than tau d, okay, in the absence of the acceptor and the presence. This is how we can calculate the experimental energy transfer and the energy transfer efficiencies, okay? So basically, we need to know the changes in lifetimes in the presence of the acceptor and the absence of the acceptor. Here we have an example involving terbium, strontium, and the terbium barium phosphates. Okay, the graphic shows the decay curves for the 5d4 level of terbium. The longer lifetimes here correspond to the samples without the acceptor, the europium in this case, while the short lifetimes are observed in the presence of the 10% of europium in the matrix. And we see here the shortening of the lifetime maintaining the same structure only with the doping of the acceptor in the matrix. And with this, we can see, for instance, the shortening of the lifetime in the from the presence of the acceptor. And with this, we can estimate the experimental energy transfer rates and the efficiencies. Okay. Well, now let's discuss how we can estimate theoretical energy transfer rates. These rates can be calculated using several mechanisms, including dipole-dipole, dipole-quadrupole, quadrupole-quadrupole, exchange, and magnet-dipole-magnet-dipole. In this equation, A represents the acceptor and D represents quantities from the donor. For instance, this Sd is the dipole strength of the donor, the electric dipole strength, and this is for the acceptor, okay? And this Q here, SQ, represents the quadrupole quadrupole strength, okay? So I highlighted here some quantities. For instance, the R means the distance between the two centers, the donor receptor, and F is the spectral overlap factor. Okay, and these equations are based on Fermi's golden rule, which provides a quantum mechanical basis for understanding transition probabilities. And nowadays, these formulations is known as Kushida-Malta model or theory. This whole FF is the overlap integral for the exchange mechanism between 4F orbitals of the donor and acceptor. And as we can see here, that this overlap decays very fast to 0 with the increase of the distance. And this is a consequence of the 4F shielding effect. Here are the complete formulation of the equations, are not in details here, but we can see that here there are Judah-Feltens parameters, okay, shielding factors here, printed here, and selection rules are contained in these matrix elements, okay. It is important to mention that I just highlight this, that the energy transfer involving quadrupole depends on these U2 matrix elements. This will be very important in the case of neodimio to iterbio energy transfer. This is an example on how we can represent the spectral overlap between donor and acceptor transitions, involving the terbium 5D4 75 as a donor and the europium 71 5D1 represented here in this diagram as acceptor transition. And the parameter delta indicates the energy difference between the donor and acceptor barycenters. And there is a formulation for that. We can estimate this spectral overlap factor in an analytical way, where we need to know these parameters, the difference between donor and acceptor barycenters of the transitions, and the bandwidth of the transitions. This is bandwidth of the donor of the acceptor. In this case, where the donor is, the energy of the donor is above the acceptor, okay, this factor G here, it should be 1, equal 1. This means that the energy transfer from donor and acceptor here is facilitated by the energy conditions. But in the opposite case, when the donor energy is below the acceptor, there is an energy barrier that depends on this delta. So basically, we need to multiply this spectral overlap factor by a Boltzmann factor, okay, Boltzmann barrier. This is represents when we have this delta negative, we see that the spectral overlap drops fast to 0. This table summarizes some rates obtained for different systems. I'd like to highlight that dipole-dipole mechanism, also Foster, has been observed to be far less effective. Instead, the exchange and quadrupole mechanism are found to dominate the energy transfer process. This is why we have certainly restriction to use it to use FRET, the dipole in the the interaction of the lanthanide to lanthanide energy transfer. It is important to mention that energy transfer rates are also thermally dependent. In this video, we can see that the emission of the compounds is emitting red at room temperature. The compound here can emit red at ambient conditions. And when this is characteristic for the europium, and when the system goes to 77K, for instance, for nitrogen, liquid nitrogen temperature, we can see more the characteristics of the terbium 3+ transitions. So there is a thermal dependence of the energy transfer. This is very important. Now illustrate some works which we adopted this theoretical procedure. This example shows a good synergy between experimental and theoretical calculations in some metal organic frameworks, where was doped with europium and terbium ions. Okay, here is the structure of the morphe and the distance involved between lanthanide centers. And here the shortest distance between 2 pairs of europium and terbium. And we calculated the terbium to europium energy transfer function temperature. And we note a good agreement between the experimental data and theoretical rates, and where this X is the europium 3+ amount in this terbium morph matrix. And we also see nice agreement with the calculated lifetimes as well. So for further details on temperature effects on luminescent thermometers, I recommend these 2 works. Okay, this is more a review. about this, and this is the paper that I mentioned with tab in Europe energy transfer. But okay, after the overall introduction of the energy transfer, let's finally see the case of neodimio to iterbio energy transfer, which is the focus of this main of this presentation. We recently published this paper about coordination polymers containing both neodimio and iterbio in different concentrations. So we try to apply this equation and see if we can estimate the experimental and the theoretical energy transfer rates. So this is the main diagram of the interaction that can occur between neodimio and iterbio. And this is the synthetic route here. I will not in detail about it because I don't know anything about it. And but there are two different compounds, which depends on the concentration of the iterbio or neodimio. With high concentration of iterbio, a central inversion starts to appear. And the emission is very, very weak. It means that Joule effective parameters are 0. With high amount of neodimio in the structure, there is no central inversion, okay, but there are 6 coordinated waters with the lanthanide ions. And this is a problem in terms of luminescence of lanthanide ions. When my colleague Miguel Hernandez from the University of La Laguna in Spain measured the lifetime of the pure neodimio sample and the other sample with small amount of iterbio, he notes a very strange behavior. And the lifetimes are in the order 50 nanoseconds, independently on the concentration of the iterbio. And there is for that the unusual short lifetime is due to the quenching produced by water molecules. So the water molecules are quenching the emitting level of neodimio. So the first conclusion was we cannot apply those equations for this specific case. And we try to see why we can estimate this theoretically. So basically, just to see the order magnitude of this lifetime, it should be in milliseconds or microseconds, not in nanoseconds. And then we estimate theoretically the energy transfer rates, and we found different energy transfer pathways, never explored in the literature. Some of them are almost 100 times stronger than this usual 4F 3/2 to the 4I 11/2. That is the standard for the literature. And we see, for instance, this 2H 11/2 to 4I 15/2 is way stronger than this pathway. So basically, we cannot use that equation because we need to, the usual procedure is to estimate this lifetime. But if we found that this emitting level is not good donor, we cannot use this. Okay, that equation works very well for iterbio and European case, but for neodimio and iterbio not. And then we can check it if we see this Harrison rules. For instance, if you consider the donor 2H 11/2 to 4I 15/2, we see that all matrix elements are allowed here for dipole, for like dipole strengths, and also the quadrupole is also allowed because this U2 is different from 0. But the case of 4F 3/2 to 4I 11/2, we see this condition. This makes elements will be 0. Okay, sorry, I did put it here, but it's different for here. So this is the main consequence of these selection rules. And we have been observing that the quadrupole is very important. And in this case of this transition, this is not allowed. Okay? So with all rates in hands, we simulated the rate equation model, considering all energy transfer pathways. And in the case of neodimio to iterbio, we constructed an 11 levels model, which consisted of 11 ordinary differential equations, each one described by this formula, the rates that enter in one level and depart from this level, okay? And the P is the population. So we need to, this is the complete set of differential equations here that describe the system, describe the dynamics of energy transfer of this diagram. And when we solve here this with numerical methods, such as Hugen-Coulter method, we can estimate the population of the emitting level of both neodimio and the iterbio. Okay? And this agree with thermometric part of the work. The thermometric properties, we can define a thermometric parameter that it is defined by the intensity of iterbio as a function of temperature. Okay, this is the emission of the iterbio divided by the emission of neodimio as a function of temperature. And then we can also calculate the relative sensitivity through this equation. So basically, we have here the experimental data for this delta and the sensitivity of the thermometer here. And this aligns very well with our theoretical prediction. This curve here represents exactly the experimental data according to the concentration. This is for 11% of iterbio, and we can estimate for close to 20% of the iterbio content in the matrix. And we note a good agreement between experimental data and simulated values. And this agreement was the first indirect evidence that the 4F3 halves of neodimio lifetimes cannot be used for the estimations of energy transfer rates. And now we are preparing new work with spectroscopy proof of the importance of this level in the energy transfer process. And this student Leonardo Saraiva, is from Brazil, but he's now in our group here in Aveiro. And he prepared some exercises to study the non-importance, or let's say no importance, of the neodimio 4F3 halves in these energy transfer processes. Basically, the idea, as you can see here, he excited at 581 nanometers and monitored the lifetimes of neodimio 4F3 halves and 2F5 halves as a function of the amount of the iterbio in the matrix. And we also calculated the backward energy transfer. It means from iterbio to neodimio, considering these two main pathways, W from 2H11 halves to 4F3 halves. And we see that a good correlation here when this increases too fast, this energy level to this energy transfer, the 4H11 halves, increase too fast with iterbio amount, we can see that there is a quenching of the iterbio population here. So they are well correlated with because faster is the energy transfer, this lifetime should be shorter, okay? And we cannot see any behavior here for the 4F3 halves is nearly constant here for long range of iterbio amount in the matrix. So to finalize, as a take-home message, fret is not important for alien energy transfer. and the is a consequence of the quadrupole, and the exchange mechanism. They are dominant, and we can model the lanthanide emission are a function of temperature, and with this we can predict the delta parameters and the accessibility of the thermometers. And we have now a new point of view regarding neodimio to iterbio energy transfer process, different from what is reported in the literature. And well, we need to take this illustration in mind, that if you are pushing this truck in this direction, this guy is pushing forward here, but there is a correlation. The truck is moving, okay, and this guy is pushing forward. There's a correlation, okay. This could be the dipole, but we need to know the causality of this moving of this truck. Finally, I would like to thank the funding agencies and the group, of course, and of course, all collaborators and friends, and thank you for your attention.
Thank you very much, Albano. Very, very nice talk. Very interesting, and a lot of quantum mechanics.
Yeah.
Now we will start with the questions from Professor Augusto Moreira from the University of Pernambuco. He's there.
Okay, hi, good morning to
Olá.
everybody, and hola.
In Portuguese, it's feel free.
Pode ser em português.
É meu conterrâneo.
Prazer em conhecê-lo. Sou amigo de Júlio também. Ele é
Sim,
nosso
sim, sim.
colaborador aqui na Federal de Pernambuco. E uma dúvida que eu tenho é a transição às taxas via regra de ouro de Fermi. Você usa uma única transição, ou existe a possibilidade de você colocar vários passos, vários steps de transições, né? Ou seja, é uma transição de primeira ordem, ou você considera segunda ordem, terceira ordem, né, nos cálculos? Isso para mim não ficou muito claro, né? Como é que, até que ordem você vai para calcular as taxas de transição usando regra de ouro de Fermi, né?
Ok. Posso responder em português? Para todos ficar tranquilo? Pode. Tá
Por
bom.
mim,
Não, então, excelente pergunta, Augusto. Na regra de Fermi, o que a gente usa é para perturbação fraca, né? Assim, fraca. O que a gente faz? A gente escreve um hamiltoniano, né? Por exemplo, interação de Coulomb. E a gente
certo.
aplica, né, na regra do Fermi. E a gente desenvolve a partir dali, por exemplo, a gente desenvolve, então, fazendo a expansão multipolar. Isso
Certo.
ou seja, a gente pode calcular o dipolo-dipolo, consegue equação, pode expandir para os outros termos, quadrupolo, por exemplo, aí temos os termos quadrupolo, né? Ou dipolo, quadrupolo, né? Então a gente depende do hamiltoniano que estamos usando, certo? Então, assim, mas a princípio é de primeira ordem mesmo, né?
Ok,
Primeira ordem,
tá bom,
né?
entendi.
Em regime de baixa perturbação, né?
Certo,
Porque a regra de Fermi é complicada quando você tem, né, uma perturbação muito forte, né? Eu acho
certo.
que já não é tão válida, né?
Uhum. Não, ok, tudo bem. Então você considera, assim, várias transições, mas de primeira ordem, né?
Isso. Então, por exemplo, aí com a equação, cada transição a gente faz, ou seja, a gente calcula a transição,
Uhum.
ou seja, vamos pensar de polo, o mais fácil.
Sim.
Calcula a, a, ou seja, a parte dipolar do aceitador e do doador, certo?
Aham.
E calcula uma taxa. Depois já faz
É.
varreduras para outras transições. E calcula várias taxas. Ou seja, tem casos, eu fiz uma vez para o iterbio europeu, que deu 3.600 taxas, só para um par,
Sim, bastante.
a uma certa distância. Uma certa distância. Então a gente muda também as distâncias, né? De tudo, né?
Ok. Tá bom, obrigado aí.
Obrigado,
Muito
Augusto.
bom, muito
Prazer conhecer.
beleza. Um assunto pesado, né? Como foi dito aí, muita mecânica quântica,
É,
mas parabéns aí.
obrigado.
Obrigado.
Now, Margarita Sanchez, do you have any questions?
Yes. Hello, good morning. Thank you for the talk. Very interesting. It's not my subject. I'm a chemist. I do synthesis, and right now I'm starting to work with MOFs, the synthesis of MOFs. And I was just wondering if you have if you have done some work on the effect of lanthanide dop MOF or lanthanide MOFs, but the effects of defects. MOFs can have like missing linkers or missing the parts of the cluster, missing clusters. I was wondering if the effects have been studied.
Yeah, for the specific case of the of MOFs, we didn't do this kind of simulation, but for crystals, we can I mean, in organic matrix, for the fluorides, oxides, we can introduce the interaction between defects.
Like
Of
vacancy.
the crystal defects, or vacancy of this kind of. But I think I believe in this morphs, we can use a similar procedure to use for morphs. Okay, but we need to know to localize the state. Okay, know the level of defects if your morph has a lot of defects or not, and how they are distributed in the morph. But it's possible. It's possible. In principle, it's possible.
Thank you.
You're welcome.
Thank you, Margarita. Now, Jaime Llanos, would you like to make a question?
Okay, thank you very much. Thank you very much for your nice talk. I have a question from the experimental point of view. When we apply some model of energy transfer, for example, we use Inoguchi-Hirayama transfer model, we calculate only from the structural model of the host matrix the critical distance from the equation of Blasi. But when you calculate it, then when you apply some different model of energy transfer, the results are quite different. How do you can explain this situation? Can you help me to understand this?
This is a very, very pertinent question. Actually, this is in my mind every day. Because, for instance, when you use BLAS, for instance, critical distance, it's complicated because, as I mentioned in my presentation, a lot of models does not include the Judah field theory in the case of lanthanide compounds. Okay, and this is essential. It's essential to include the Judah field theory to explain with more correctly the transition FF transitions. Okay, but the critical distance is given by dipole mechanism. You know about that, right? You see the dependence of R to the power 6 in the critical distance, and this I think this is not correct because they are considering only dipole, and we have been observing that for the case of lanthanides, okay, dipole contributions are not important due to the selection rules, due to the nature of FF transitions, the dipolar nature of the FF transitions, they are forbidden. a priori. So
Okay.
in the case of Inuyama, you can use the lifetimes, and you see some factors that they say are, if you fit with R to the power 6 is the dipole. It's if it fits the parameter, the Q parameters, or 8 is dipole, quadrupole, and so on. This equivalent to what we have done, but we are calculating without uh, any experimental data from the theory. Okay, and this is complicated because I put in that part of correlation and the causality. Okay, the dipole can be a good correlation with the efficiency of the energy transfer. Of course, if dipole increases, the energy transfer can be increased as well. But is this the main factor that is influenced in this energy transfer? We have may observed that's not. This is the quadrupole, and the exchange mechanisms. Okay, so
Thank you.
basically these models have this trick that I think in the near future some people will start to see that's this different nature of lanthanide ions.
Okay, thank you so much.
You're welcome.
Thank you very much, Jaime. Now I ask Mario Reis from Brazil if he has some questions.
Hello. I don't know if I
Hello.
speak in English. I usually speak in English here in the network, mas seguindo o meu colega anterior, eu vou falar em português. É, é uma grande surpresa ter um colega de Aveiro. Metade da minha vida foi em Aveiro e metade da minha vida profissional e pessoal foi em Aveiro. Envia um grande abraço para o Luiz Carlos, é um grande amigo. E para
Sim.
todo o pessoal do departamento de física, muito carinho com. Minha família, inclusive, mora em Portugal, em Aveiro.
É?
É,
Ah,
é, deixando a parte pessoal de lado, eu tenho algumas perguntas. Eu vou colocar as perguntas e depois o Albano, por favor, se puder responder na sequência. É, Quando você apresentou as regras de seleção para a parte magnética, você apresentou com L mais 2S. Por que você não apresentou com o momento magnético total GJ? Essa é a minha primeira pergunta. Ou seja, com o momento
certo.
magnético total, né? Ou seja, com o fator de Landé e o momento magnético total. Essa é a minha primeira pergunta. A segunda pergunta: as regras de seleção dependem do material? Ou seja, elas dependem do tipo de terra rara? Essa é a minha segunda pergunta. E a terceira pergunta qual é a barra de erro do termômetro? Vocês, no final, o objetivo é chegar num termômetro. Esse é o objetivo final. Qual é a barra de erro do termômetro? E em comparação com outros termômetros comerciais.
Certo. Bom, a primeira pergunta, né? O que a gente usa é o GS, o 2, né? É o 2,0039, o GS, não é o GL, não, né? Entendeu assim?
Não, na regra de seleção você coloca L mais
Ele mais
2S.
2S. Então, aí aquele o 2 é o GS, que a gente aproxima para 2.
Mas
É o,
depende do fator de Landé.
Então, mas nesse daí, no caso, é o giro magnético do elétron, não é o total, não. Certo? A gente usa função de ondas no acoplamento intermediário, certo? Para fazer copiar, para calcular o elemento matriz, certo? Então, assim, o que está ali, esse daí, o de Landé, vai depender do campo magnético que você está aplicando, né?
Esse campo magnético é atômico.
É,
Não há um campo externo.
não.
É o campo magnético atômico.
Exatamente.
E o multipleto é um multipleto fundamental.
Sim, sim,
Vocês
exatamente.
não consideram o multipleto excitado.
Não, não, não.
Tá, tudo bem. Tudo bem. Tá. Essas regras de seleção dependem do tipo
A sua
de...
pergunta, né? Pronto. Olha só, a regra de seleção vai depender da transição do número J, do número quântico J. Ou seja, você tem uma
Ah, tudo
transição,
bem. Não, tudo bem, vai depender do J, mas a construção da regra de seleção não vai depender do material. Uma vez
não do
construído,
íon.
a tolerancia é
Exatamente.
sempre a mesma.
Isso. É para qualquer íon, aquela regra de seleção, só vai depender do J.
Tá,
Aí cada transição vai ter um J diferente, delta J, um J',
tudo
né,
bem,
enfim.
tudo bem. Ou seja, a estrutura é a mesma, só muda o J, porque cada íon vai ter um J específico.
Isso, exatamente.
Tá,
Né?
tá.
O
E a
que vai
barra de erro?
mudar,
Não,
rapidinho,
entendi,
o que vai,
entendi. Uma vez feita a regra de seleção, muda o íon, a posição vai estar a posição da regra de seleção vai estar em lugar diferente por causa que vai ser um íon diferente.
isso,
Porque
mas assim,
cada íon tem um J diferente.
Mário, mas é importante também que a simetria, aí sim, você depende do material, vai estar nos parâmetros de Dirichlet, nos ômega lambda, certo? O que é que você tem a regra de seleção no elemento matriz, os U lambdas, certo? Que depende do J, e vai estar multiplicado isso aí pelo ômega lambda, que é os parâmetros de Dirichlet, que depende aí sim de simetria.
Parâmetro de campo cristalino.
Isso, exatamente. Né? Ou campo ligante, né? A gente usa o termo campo
É o
ligante,
campo
mas
ligante. Tudo bem,
é.
campo ligante.
Pronto, mas é isso, é basicamente isso. A parte de simetria vai estar no campo cristalino, que é os ômega lambda, e a resseleção vai estar nos U lambdas, né? Que
Tá,
aí tem
tá,
trabalhos que já tem tudo, assim, tabelas, são tabelados para cada transição, cada lantanídeo.
tá, entendi. Tá,
Né?
ok. E pô, a minha última pergunta é a barra de erro do termômetro, da
Certo. Pronto.
temperatura.
Então, e isso, a barra de erro do termômetro da sensibilidade, tá falado da sensibilidade, não é isso?
Sim,
Sensibilidade
você
reativa.
mediu 200 Kelvin. Qual é a barra de erro?
Pronto. Aí é o seguinte, isso vai depender do equipamento, do sinal, da razão sinal-ruído do equipamento. Eu não mostrei aqui, mas tem um parâmetro que eles usam que é a incerteza, certo? Porque aí isso é experimental. Isso aí é depende do equipamento, eles têm a incerteza na medição. E eles fazem a incerteza de acordo com a temperatura, certo? Nesses artigos aí, eu posso até enviar para você, tem como eles calculam a incerteza, certo? Aí sim, a incerteza é outro parâmetro, mas essa parte experimental. Vai depender do equipamento, do sinal,
Mas é
ruído.
da ordem de quanto? Você
Hum,
tem noção?
o décimo de Kelvin, talvez.
Tá.
Depende muito da precisão do equipamento, né? Da
Ah, mas
resolução
em
do
ordem de
equipamento.
grandeza, para 200, vamos supor, para 200 Kelvin é um décimo de Kelvin.
200, mais ou menos 0,1, 0,2, sei lá, algo assim, por aí,
Tá.
né? Às vezes, depende do equipamento, se for mais portátil, um aspecto mais portátil, chega a um Kelvin, 200, mais ou menos um Kelvin, certo?
Ok. Beleza.
Então,
Obrigado. Abraço.
Thank you very much for the interesting discussion in Portuguese. Now, Sergio Conejeros, do you have any questions?
So thank you very much for your talk. I think it was very interesting, and I thought that you gave a very nice introduction in a topic in which I'm not expert. My first question is about how do you calculate or which code do you use for calculating the Doppler parameters? So do you use your own code or do you use a code that is being developed for another group? Can you give me some details about
okay,
that?
okay, thank you for this nice Nice question. Actually, for the Julia-Felt entities parameters, we used our own platform. This is free online, or you can. I think I put one slide here just to show you about the Julia-Felt. I don't know. Okay, no, this is not here, but okay. We use the GeoSpectra web platform. I can send to you the address. It's a web platform that you can insert in your structure in the website. They will require some parameters, or if you have experimental parameters, you can put there, and the program can calculate also the energy transfer. Okay, for this case, it's not specific for lanthanide, but for the interaction between ligand and lanthanide. Okay, but we use it. I answer your question is we use a web platform that we are developing. Okay, GeoSpectra.
Okay. Can you share the link, or this is the address in the website, the ciseco dot.
No. There's not the. I think now the GeoSpectra is under maintenance because we are including, but I can put the name here in the chat. I think it's better.
That would be great.
Yeah. The service down. Okay, now is not online because we are updating the platform, but you can search this in Google. You can put GeoSpectra, and you can see.
I know. Yes.
Okay, but yeah, this basically we use this platform, and this platform is very useful for we have more than almost 200 users around the world. Some people from China, from USA, and are using that and applying for calculate energy transfer.
And compared to other kind of software or similar software like Relic, have you ever heard about Relic?
Yeah. I heard Relic.
No, and there is another one. Is
Maxwell Helen.
So, how is your code compared to this?
Lumpac. Yeah, actually, I talked with Marcus Helen from the Relic a long time ago. I sent an email asking for I need some matrix elements. Can you provide this? And he told me that unfortunately the project was closed. And he said that he is not allowed to make new versions. There are some bug fixes with the Windows, and he gave up this project of the Relic. And the Mopac, I know the guys here. They are also from Brazil. Okay, and I talked with one of the creators of Lumpac a lot by WhatsApp and so on. And but the Lumpac is okay. There's some issues in Lumpac that for GeoSpectra we can calculate for any lanthanide ion. Okay, because we estimated these matrix elements and introduce it in the code. And the Lumpac you can only calculate it for the European.
Yes, I have heard about that. Yes.
Yeah.
Yes.
Up to now, it's from Europe. I know that Diogo, one of the creators of is working to include the determined ion. Okay.
Okay, thank you. And my last question is regarding about. So you know the calculation of the utilization parameter. Do you obtain that for you obtain that for when you do the model fitting. But have you tried other kind of approaches, more accurate approaches, like using quantical mechanics methods? I don't know, DFT, is quite
Yeah,
limited. But other kind of approaches like a post-Hartree methods.
KCF maybe. KS
But
calculation.
yeah, with post-Hartree method, you can use them for calculating complexes, or a dimensional system like molecules. But for material is you need to cut
Yeah.
the materials. But have you tried other kind of approaches or like that?
I didn't present here this presentation, maybe in another opportunity, but we can calculate the energy transfer from ligands to lanthanide ions. So in this case, we estimated the excited states we using TD-DFT.
Yeah.
For the part of the ligand, and we can see how the excited state is localized, and we can extract the donor receptor distance.
Okay, and the difference, because you need to cut the crystal, right? So
It's a nightmare. It's a nightmare.
Yes.
For me, it's a nightmare.
How accurate are the results? No considering the periodicity of the crystal, just the
Depends on if you are dealing with molecular. Okay, you can isolate it. You can get the crystallographic structure, for instance, or you can extract the one molecule, okay, that represents your model.
But when you have like an inorganic crystal,
so it's a nightmare. It's a nightmare.
Are you able to obtain good results doing the cluster of the
really?
Are you able to obtain good results, or it could, because when you cut the crystal, it's a nightmare. But is it worth it to do it, or not? The results are good enough.
Actually, I think you can use periodic conditions to do that. So, but for me, it's a little bit far from my expertise. I have colleagues that can calculate this. Okay, using periodic boundary conditions, and can replicate it and calculate the energy levels and so on for this. But this is out of my expertise. But I knew people, if you know how to model this kind of systems, maybe we can talk.
No, I'm just asking you about so I would like to know if it is worth it to do.
Yeah, it's possible, but it's complicated.
Okay, thank you very much, Albano.
Thank you.
Sergio. Arturo Martinez, would you like to make a question?
Thanks for your talk, Albano. I don't have questions. So, thanks.
You're welcome.
Okay. Well,
I have a lab question, please. It's a practical question. How do you think about the fiability of the experimental J-Doppler parameter obtained from LUMPAC in the case European?
It's well, I think it's a good approach. This approach of the obtention of the J-Doppler intensity parameters from the emission spectrum. It works only for the European. Okay, due to selection rules, there are some constraints that allow to do that for the European. But for use LUMPAC, I think it's okay. For instance, I never heard. I don't use LUMPAC, okay, but I never heard about problems with the extraction of J-Doppler parameters, experimental J-Doppler parameters using MOPAC. I never heard about. if there's any problems with that. Yeah, actually now we are because the George Spectra platform is more for this is more a platform that we are develop for including others lanthanide ions, but it's complicated to calculate the energy, the Judah-Feld parameters for the other lanthanide ions, because we need to know the absorption, the oscillating strengths of some materials, and a lot of them may overlap with the FF transitions, with the ligand, and so it's complicated. But for open, it works very well.
Thank you so much.
You're
Right.
welcome.
There is a question from the chat in YouTube. If it is possible to calculate the lifetime, the luminescence,
Yeah.
how do you do it?
Yeah. Okay. The lifetime, okay, we can calculate the lifetime. We know the relative decay, okay, using Judah-Feld theory. We can calculate the radiative component, and then we can estimate the non-radiative part. Okay, the lifetime will be the inverse of these contributions of the radiative and non-radiative component. So in this case of the radiative, Judah-Feld. In the case of non-radiative, we need to know we need to use, for instance, the energy gap law, or some model that take into account phonons that can be coupling with the electron phonon coupling, and we can estimate the decay, non-radiative decay. So it's possible to calculate lifetimes, but this non-radiative part is a very complicated.
Can be
Depends on the material a lot.
can be produced with this time-dependent DFT calculations, do you think?
Yeah, if you do some kind of frequency calculations, you can know more or less the main energy of the main phonon energy of some vibrational contributions that can coupling with the electronic states, the emission electronic states, and then we can use it. We can apply this energy and the number of phonons in a multi-phonon relaxation.
Okay, interesting.
Yeah, there are models for that. I can mention Miyakawa-Dexter model. It's very useful for that. We made some estimations. I don't know if I have here. Let me check.
Yes. If not, I will ask you for the papers.
Yes, yeah. Yeah. Here is. Here. Then we can use energy gap law. According to Miyakawa-Dexter model. This is one of models. There are a lot of models that we can use, but basically we can calculate the non-radiative relaxation rate, okay, from the upper level to the lower level. Will depend on this delta E and this alpha parameter. That depends on the, for instance, one Higgs factors, the occupancy of the phonon using a Bose-Einstein distribution, the number of phonons involved in this gap, the energy of the phonon. So with this, we can estimate the decay rate here. The decay rate. And together with the relative rate, we can estimate the lifetime.
Right. Great. Thank you.
You're welcome.
There are any more questions in the other chats? If not, I would like to ask one more question. Which code did you or your colleagues use to do this time-dependent DFT?
Yeah, usually we use Gaussian, Orca.
Orca,
No,
that was
yeah.
molecules. Orca.
Yes,
Right.
yes. And nowadays we are migrating to Orca because it's a free program. We don't have problem with the
Yes,
this
it's fashion
license.
Orca.
Yeah.
Okay, thank you very much. If there are no more questions, would you like to say some words? Perhaps we can open our cameras to thank you for your very nice talk. Very
Thank you.
interesting from every point of view, experimental calculations, quantum mechanics.
Que ya
Okay.
puede dejar de compartir su screen, Albano.
You can stop sharing.
I will. Okay. Okay?
Sí, está bien.
Okay.
¿Você desea añadir palabras de despedida a la red?
I'm sorry?
Or would you like to say some goodbye words to the
Yeah.
network?
No, I would like to thank the opportunity to be here for the invitation to talk about some progress we are made in here and in the context of lanthanide ions. Okay, and so I'm very grateful for kind invitation and this nice audience that with a lot of interesting questions and discussion, and thank you.
Okay, thank you very much. You can open your microphones and to say goodbye to Albano, please. Abran sus micrófonos para decir hasta luego, Albano.
Okay.
Bye, Albano.
Bye, Albano.
Bye.
Thank you. Thank you so much.
Hasta luego.
Thank you.
Cuídense. Chao, chao.
Adiós.
Chao.
Chao.
Adiós.
Puede dejar de compartir Ximena y Melvin.